that. So he's a systems engineer for Voxel. They're innovating on voxel engine technology, the ability to actually make games, for example, and other interesting 3D projects just using pure voxels, right? So I think that's great. You know, lots of companies have tried and failed in the past to make voxels, pure voxel engine tech work, right? So they're trying to crack the code there. And then he has a talk called Optimism and Design. I don't want to spoil it. So his first time talking, first time as a speaker. Let's be warm and welcoming. A big round of applause to Davis Morley.
So I do want to clarify, although at Voxel we do work on like pure voxel engines, I'm going to be covering a more rasterized version of voxel engines for the sake of the talk. But
that works too.
All right. Well, there you go. There you go. All right. So today I'm going to talk about optimism and design. So I want to take you all through the process of creating a voxel engine together, and so we're going to have to start with the basics. What even is a voxel? This can be a pretty contentious idea. If anyone's had an annoying conversation about pixels before, just take whatever you think about pixels and apply that to 3D, and you're right, okay? But I'm also going to define it for the sake of this talk, you know. Let's just say our voxel is a point in a 3D grid, all right? It's just a cell in this uniform grid. Well, what space does our grid exist in? What kind of world does our voxel exist in? Well, we know it's a 3D grid, so we have 3 axes, x, y, and z. But let's define our horizontal axes as x and z, and our vertical axis as y. Okay, but what kind of data should our voxel have? Well, let's say we want a dynamic world, we want different kinds of voxels, we want variation. So let's have some different voxel types. What kind of voxels do we want to start with? Well, let's just say we start with stone, dirt, sand, and grass, all right? But we need a way to uniquely identify these voxels, right? Because we have these 4 types. How do we know which voxel our voxel is? What we can do is we can assign unique identifiers, right? So we can assign stone to 1, dirt to 2, sand to 3, grass to 4, and then air to 0, which is really just the absence of a type. Okay, well, what does our voxel look like in memory? Let's just say it's an unsigned 16-bit integer, all right? And it just has this ID. So now we have a voxel with its type in a 3D grid, and this 3D grid exists in this space. But what is our volume? What kind of world do we want to have? What volume is this single voxel a part of? Well, instead of having one massive world, if we think about it, voxel engines are normally very localized in their changes. When you place and break a single voxel, they're very local in scope, right? Even if you have voxels act on their own, they're always going to be affecting a very small, specific region. So instead of having one massive world, what we can do is we can break it up into smaller chunks. And you might have heard the term chunk before, and this is where it comes from. And now when we change or replace voxels, we can be very focused on how we update things. We only have to care about the actual region that it's affecting instead of the entire space, recontextualizing all of it, right? What size should these smaller chunks be? It's kind of a balancing act, right? Because as a programmer, we have to consider how many unique objects we want to reason about in our code, and also how large of an area we want to have to recontextualize when we change something. Well, I decided for us for convenience later on, so let's just go with the size of 64. And all this means is we have 64 voxels in every direction, x, y, and z. Or we have a 64 cubed volume, or 262,114 voxels. So now our voxel world is made out of 64 cubed chunks, right? Well, what does our chunk look like in memory, right? We know what our voxel looks like in memory, but what does our chunk look like? Well, we might initially go with the idea of using a 3D array where we use a voxel's position to index into a specific voxel. But that's kind of annoying because whenever we want to refer to a single voxel, we have to lug around this position. So what we can do is we can take that 3D position and compose it into a single digit that we can use to index into a flat array. Well, how do we do that, right? Well, to start, we can break down our index into single axes, right? X, Y, and Z. And we can compose it from there. So let's say we start with X. Right now, we are just creating our index from X, so any addition to X is really just an addition to index. +1 to X is just +1 to index, right? Which means index is only going to be 0 to 64 because we can only have X be 0 to 64 because our chunk size is 64, right? And next, let's add Z. We could have chose Y, but for the sake of iteration times and cache coherency, let's say we chose Z, right? So since our chunk size is 64, and X is always going to be in the range of 0 to 64, what we can do is we can add z to our index without actually affecting our x value. Our x value is always going to exist in that 0 to 64 range, whereas our z can exist in a 0 to 64 times 64 range, right? So whenever we add 1 to x, it's just actually adding 1 to index, and whenever we add 1 to z, it's actually adding 64 to index, because z is going to be a multiple of 64. And that way we're not creating any extra voxels. We still have the same amount of voxels, right, because we're creating a 3D volume, but we can still extract the parts we care about later on. So now we finally add y. So we've covered the range of 0 to 64, and then 0 to 64 times 64. So now we can cover the range of 0 to 64 cubed, right? So now any addition to y is really 64 times 64 in the index. So we can compose it all together. And now we have our finished formula, right? We have x, y, and z all adding to this formula. And we're only affecting specific ranges per type of axis, per axis direction. Well, how do we get our index back to 3D position? Well, since we are only affecting specific ranges when we create our index, we can also extract those specific ranges when we want to care about a certain axis, x, y, or z, right? Or all together. And we can do that by, since x is actually just 0 to 64, we can see we can just take index and use the modular operator with 64 and extract that 0 to 64 range. And since z only exists in a range of 0 to 64 squared, we can do the same thing where we divide index by 64, then use the same modular operator, and then we just repeat that process for y. So we're still representing a 64 cubed area, but we're now able to use a single position, a single index from this 3D position, right? So now we can define what our chunk looks like in memory. Instead of having that 3D array as before, we can just have a single index in a flat array, which is really powerful because now we just have this handle to this voxel. Well, what about our world? Well, we can take the same concept we had before of taking a 3D position of a voxel and turning that into a single index and apply that to our chunks. We can take our chunks 3D position in the world and turn that into a single index into our world's own array of just chunks, right? And we can do this the same way we did it with 64 before because we knew our chunk size was 64. We can take the size of our world or the render distance in any given direction and use that to compose our chunk index, right? So now that we have everything in memory, right, we've defined our voxel world. What does it really look like on the screen? How do we take this and put it on the screen? Well, let's start with a single voxel, right, the simplest form that our engine is going to render, right, at any given time. How is a voxel going to be represented in our world, right? Well, for the sake of simplicity, and this is where it's no longer a pure voxel engine, so to speak, let's just say our voxel is geometrically a cube. Well, how do we draw a cube on the GPU, right? What we can do is we can take its 6 faces that make a full cube and break those into triangles. So now we can draw 12 triangles for 6 faces. When we add them to all together, we have a completed cube. But what are our triangles made out of, though? Vertices, right? We have these corners that we're constructing these triangles out of, and then constructing these faces out of, and then eventually, when we combine them all together, we have a single cube. So what is our vertex made out of? What is the simplest building block that we're using to construct all this information made out of? Right? Well, let's just say, well, what information do we really need to convey to the GPU when we're drawing a single voxel? Well, we need to know where it is in the world, so we need our x, y, and z. And we also need that index. And we also need the ID that we defined earlier of, dirt, sand, grass, so that we can properly texture it when we draw it. Because we need to know, if I'm dirt, I want to look like dirt. If I'm stone, I want to look like stone. And we can convey that to the GPU with this ID. Okay, so now we can draw a cube, or we can draw our voxel, finally, right? We have our vertices, we have our triangles, our faces. But how do we do this for the entire world? Well, if we took that same concept of adding 6 faces for every single voxel that had a type, it wouldn't work very well, right? Because what are we really trying to do here? We're trying to extract the simplest form, the simplest geometric representation of the world that we can. And right now, if we added 6 faces for every set voxel, we'd have a lot of occluded faces, or invisible faces, right? So what we can do is, instead of adding every single possible face, we only have to add faces that are exposed to air. So instead of adding these redundant faces, we only extract the parts that we care about. We only extract the parts that are ever going to be visible to the camera, or the player in this case, right? And this is called naive meshing, because we're doing the very first naive thing. We're just getting rid of the data that we don't need and holding on to this data that we actually care about. So now let's do this for every voxel in our chunk. So we just go through everything, we extract all the faces we need, and if we do that long enough, maybe we don't add some faces for a single voxel, but if we combine all the actually visible faces, we'll have a completed representation of our chunk, even though it's like a sparse extraction of vertices, right? Great, so now we're done, right? Well, we just defined what our voxels are in memory. We just said how we can render them. We can extract the faces we need. Well, it's kind of slow. Naively meshing a 64 cube chunk, or our chunk size, takes around 3 to 5 milliseconds on my i7-8700K, right? Which isn't the best CPU, but it's not the worst either. And when I draw that same test with a simple testing with 1024 by 255 by 1024 resolution that contains just a simple flat height map essentially, I get around 55 FPS with an RTX 2080 at 720p, which sucks, right? That's really, really slow. We can do better though with something called greedy meshing. So what exactly is greedy meshing? Greedy meshing is where we take adjacent faces that have the same ID and combine them. Well, how are we able to do this? Well, if we think about what data we're actually uploading to the GPU, it's just the position so we know where the voxel is in the world, and the ID so that we know how to properly texture it. So if we have adjacent faces, we can represent that same information with a single face combined, because we can just enlarge the area that single face is covering and also keep that same ID. If they're all sand, they can all still look like sand, and we can represent all of them with a single face. That's great, but how does it actually work? Well, to start, let's just take a 2D slice of our world. It's easier to do things in 2D first and then translate them later to 3D. And to start, we can focus on those sand blocks in the bottom left. And then we'll also start growing from the bottom left voxel, the bottom left sand voxel. So we know we have an ID of 3, and what we can do is, let's just say we try to grow this face first vertically, right? So what we can do is we can look at the voxel above us, and if it has the same ID, which in this case is 3, if it's also sand, we can grow to it, right? But if we try to grow vertically again, we can see that we have air above us, or 0. Right? So we can't grow vertically anymore because we can't combine the faces because it has a separate type, and also air just simply doesn't have a mesh representation. So since we can't grow vertically anymore, what we can do is try to go horizontally. And thankfully, the next column, since we've grown, since our face is too tall, we look at the next column that's also too tall and say, hey, can I mesh to you, right? And since we all share the same ID, we can mesh. And that's how we extract this face. We essentially start from the bottom left and grow upwards and then horizontally, right? Let's apply this algorithm to the rest of our scene. Nice, it's a really significant reduction in faces. You can see that we went from 24 down to 9 in the simple 2D test scene. And if we consider for a second that our actual world is 64 cubed, and our max slice that we might be doing this on, our max 2D slice is 64 squared, it's a really huge reduction in faces, down from 24 to 9 if we were just doing naive meshing. Can we do better though? This is something I want to talk about is, if you continually step back and reevaluate your problem and think that there might be a better solution, it's a very powerful position to be in. And that does require a certain amount of optimism. You have to think that it's possible for you to do better than you're currently doing. That's kind of the theme of this talk. Well, what are we currently limited by? We have all this type information, right? We have sand, dirt, and these all have their own IDs. And we're only able to combine adjacent columns, and also only do that by considering the correct IDs, right? We can only combine sand, we can only combine dirt to dirt, for instance, right? Well, what makes up our vertex, right? Our position and our ID. But if we think about it, right now we're considering the ID when we don't really need to. Right now we're baking the ID into our vertices to upload them to the GPU so that we can texture them properly, but we only really need that ID on the GPU, right? We're preemptively preparing this data, even though we only really need this data on the GPU. So instead of preparing it now and meshing, what we can do is we can just upload it directly to the GPU. So instead of having to consider this on the CPU or local in memory when we're meshing, we can just have this type buffer directly on the GPU and sample it that way. We could also have it be a 3D texture, so you can just use your world space position in a shader to look up what type you are and then use that type to texture yourself. Or we could use a buffer, and that has the advantage of maybe being able to run some compression on it, like run length encoding, right? We aren't getting rid of any data, we're just moving it around. We're just taking the data we had on the CPU when we were meshing, and we're moving it to the GPU to sample there, right? So we're just moving it to where it was actually headed already. Well, where does this leave us, right? Now instead of only having to mesh similar types, what we can do is we can mesh all types together basically, because it's become a binary problem. No longer do we have to consider the type information when we're meshing because it's on the GPU already. We don't have to worry about it anymore, it's already there. So now what we can do is we can combine every single possible face. We can grow as much, or possible ID, we can grow as much as possible. So you can see we go from the left scene, which was considering type by type, to the right scene, which is just a binary operation. We start from the bottom left, we grow vertically as much as possible, and then we go horizontally as much as possible, right? So we're always continuously reducing the amount of work we're doing, and we're representing the same data though. And this requires a step back and kind of reflection that's required to really make sense of this stuff, right? Or to think it's even possible. Okay, but do we still have to work with IDs? If it's a binary problem, all we need is a binary representation of our scene, right? If we're only binarily considering types, we don't have to use that type information. We can just use bits, right? Because that's the simplest form of a binary operation, just 0 or 1. Let's think about this for a second. Right now our chunk is stored in a 3D grid of voxel structs in an array, right? We just have a single struct per voxel, and that struct has an ID. What we can do instead is we can, as a binary representation of our voxel data, is just use an array of bits. Instead of having a single struct per voxel, we can just have a single bit per voxel, and we can use that to mesh instead, right? So let's make a bit array. First, we can take our current index formula and chop off the y. So now we just have x and z. And then we can use x and z to index into a specific column. And in that column, we can bring back y and use that to access a specific voxel at a height. So let's say we have an x of 0 and a z of 0. We can use that to access the column at 0, 0, and we can use a y of, let's say, 3 to access the 5th bit there, and either set that to 1 or 0 based on if we're setting a voxel to anything besides air or air, right? So now that we can, let's turn our scene into binary. We have this bit array, we have 1 bit per voxel. What we can do is we can take any voxel with any type at all and set them to 1s. And we can set any voxel that has a type of air or 0 to 0, right? And we can see this represented here with white boxes for 1s and empty boxes for 0s. Before we combine our faces though, what are 64-bit integers really great at? Bitwise operations, right? They're perfect for the single operation comparisons, right? And if we think about it for a second, all we're really doing with our greedy meshing algorithm from before is we're doing bitwise ands. We're growing vertically, then when we have that data, we go to the next column and say, hey, do you contain me or more than me? Do you contain me at least? And we can do this all in a single operation now. We have these columns as a single object in memory. We don't have to do this voxel by voxel. We can consider it all at a column at a time, right? So we take our first column here. We skip the process of growing vertically because we already know we have 2 first set bits, right? And then we can just grow as we did before by anding that to the next column that we want to grow to. So we're really doing the same operations, but now it's just a single bitwise and. We take our column, we go to the next one, and we try to and with it. And if we can, if it contains us or more than us, if it has a height equal to or higher than us, then we can grow to it. And if we continue this process for the rest of our scene, we can see that we extract that bottom face the same way we did before if we were to consider it type by type. So we're really like capitalizing on the binary nature of this. We can use these bitwise operations to consider 64 voxels at once, right? So yeah, we've significantly reduced the amount of operations. Instead of having to grow voxel by voxel potentially 64 times in our actual scene, what we can do is we can consider 64 voxels at one go. And then we can continuously do that. So it's kind of an exponential problem. Instead of, like, if we grew vertically 64 times in one column, we would have to go to the next column, and when we were trying to grow our face to that, we'd have to count another 64 voxels. So now we can just do it column by column. It's a lot simpler in memory. It's just one operation, right? It's very powerful. All right, but there's a property of voxel worlds that we're ignoring. They often have a more complicated 3D scene, right? They're rarely this flat in nature. They're rarely essentially 2D, right? So what we can do is we can add some clouds with an ID of 5 and put them up in the top left corner of our 7x7 test scene. If we take that scene and turn it into bits, we can see that the same thing we were doing before with the bitwise and wouldn't work anymore with these 3D or more complicated columns because we can't extract one face per column, right? We have multiple faces per column potentially now, right? Well, we can make our bitwise and system work by breaking our current columns down into smaller parts. How can we extract the first 2 set bits here? How can we take the max that we were using to compare with before from our current more complicated scene? Well, we can use something that 64-bit integers are also great for, intrinsics, right? They're perfect for this. specifically one called trailing zero count. This just works on 64-bit integers. To start, we can take the first column that we want to extract that bottom mask out of and invert it. Then we can count the first series of zeros, which is our first two set bits inverted, which in this case is 2, right? And then we can just construct a new mask based on that series of zeros. And now we can use this mask to compare as we were doing before. So now we can extract the parts of the column we actually care about and use that to mesh, right? So we're getting the same result as we did before because we're only using this subset of the column. To get to the next set of the bits that we want to mesh, we know we already meshed the first 2 bits, so we can skip those, and then we get the count of zeros between us and the next series of bits. In this case, that's 3, so we can just skip those, and then we have an offset of 5 bits, right? And then we can repeat the process we used before to extract those 2 bits, right? And then we can construct this new mask out of those 2 bits and use that to mesh, right? So we can break down our more complicated column into 2 parts, and individually, when we combine the results of them, we get our completed scene, right? If we continue this for the rest of the scene, we have our completed scene. It's binary, it's fast, wow. We now have a more complicated scene, meshed binarily, using bitwise operations and intrinsics, right? So that's really, really fast, probably, because these 64-bit integers are perfect for that. So let's talk about speed. Whoa, that's fast. All the greedy meshing times, or even our naive meshing, which is like our simplest scenario, took around 3 to 5 milliseconds for a 64 cubed area. I even took those greedy meshing times, and I think it was for a 32 cubed area, but I wasn't sure about the time, so I just quadrupled them to make sure that it was accurate. Now we're down to 0.12 milliseconds for a 64 cubed area, because we've taken our problem that was considering all of our voxels voxel by voxel and broken it down into doing it column by column, or 64 voxels by 64 voxels every single time. We've greatly reduced the amount of operations we're doing. And not only that, these are really, really fast operations that we're doing on the CPU. They don't take like any cycles, right? Bitwise AND is like nothing, right? So if we expand this exponentially, it really has huge implications for our world, because now we don't have to spend potentially 5 milliseconds of our 6.7 milliseconds of frame time if we're targeting 144 FPS to mesh a single chunk. We can just mesh as many chunks as we want effectively. But we could be faster. With a simple thread queue on my i7-8700K, we can go from 0.12 milliseconds down to 0.01 milliseconds per 64 cube chunk on average. And we're able to do this because our chunks are inherently prepared for asynchronous work, right? Because all of our voxels are isolated in a single array, and all of those voxels are isolated in a chunk array. So whenever a chunk is being meshed, it's only accessing its own data. It's never looking to other chunks. It's only working on itself. So all we have to do is we can create a simple queue system of chunk indices, the same way we took the 3D position and turned it into a single index. We can add those indices to a single array, and then when a thread wants to do more work, it just has to go into this array, get that index, and say, hey, mesh me. And then from that, we can create a unique vertex buffer dedicated to each chunk, right? So that's how we go from 0.12 milliseconds to 0.01 milliseconds, and that's only because I have 6 cores on my i7-8700K instead of something more, which means 12 threads. So that includes the main thread. There's another caveat here too, though. This only works in our best case scenario when we have at least 12 chunks to saturate all of our threads. But this is kind of the case you want to optimize for. When you're loading new chunks in the world, when you have a rolling world and you want to pull in new noise or something, that's really your worst case, especially if you considered before that 5 milliseconds, you would see them slowly load in. But now we can do this in a single frame, 12 chunks at a time, in 0.12 milliseconds. It's really powerful. And then if you do have your worst case, which is where you're meshing only a single chunk per frame, it's only going to take 0.12 milliseconds still, which isn't going to hurt your frame budget much at all. Whoa, that's faster. So again, we went from 3 to 5 milliseconds down to 0.01 milliseconds. That's a huge reduction in time. But we could be even faster. If we think about it for a second, what are we really doing with our meshing? All we're doing is we're telling the GPU where a possible voxel can exist. Since we moved all the type information that we were before baking in our vertices to the GPU, we're just putting it on the GPU. All we're really doing is telling the GPU where to check this type buffer for if a voxel exists. So there's no reason we can do this also for air voxels, right? So instead of only telling the GPU to look at voxels that have a specific type, we can also tell it to look at air. So instead of having to mesh at all now, we can use a single face for an entire slice of voxels and have that work. And we make this work by, instead of if we index into an air voxel, all we have to do is discard that pixel and continue, right? So now we have a single face for our potentially 64 squared face every single time. We don't have to mesh at all. So we've gone from 5 milliseconds potentially to 0.01 milliseconds to nothing. So it's really powerful, right? Let's do this for an entire chunk, our entire 64 cube chunk. We can go from any number of binarily meshed, greedy meshed faces down to a static 64 times 6 faces. And we need that times 6 because we have positive and negative directions in every single axis, x, y, and z. So we have positive x, negative x, etc. But yeah, we went from any number of faces down to 64 times 6. That's nothing, right? That's literally nothing, basically. Let's use this for the entire world. If we think about it for a second, there's nothing stopping us from using these static faces for the entire world, right? So I call this the global lattice, because we have all these intersecting faces representing where every single possible voxel can exist. And we can know where every single possible voxel exists because they exist on a uniform grid. We know where every single face can exist because they're all uniform in space, which means we can just statically create a representation of our scene and basically render into it using this type buffer on the GPU. So with a world size of 8,192 by 255 by 8,192, the binary greedy mesher with that same like 8K height map loaded produces 35 million faces, right? But with the global lattice, or our static mesh, we only need 8,192 times 4 plus 255 times 2, or 33,278 faces for the entire world. So we've drastically reduced the amount of faces we need to represent our entire scene. And more than that, we don't even have to mesh anymore. We don't have to spend any frame time at all meshing these chunks because we can use this static representation. We know every single possible combination of our world already, so we can just represent that statically with even less data. It's really powerful. And we've kind of gone this roundabout way of having to consider like meshing and speeds and all this stuff and complexity of our problem. It's pretty complicated to do that bitwise thing I was talking about before, to completely reasoning that part of the pipeline away. Right now we only have to have a static representation that we can do on startup of faces that you can manually type the vertex positions for and use those, right? It's really powerful. So yeah, what does not having to mesh mean? Instead of having to mesh every single time a voxel changes, which could be like placing, breaking, or having a voxel act on its own, the change itself is the only update we need. That simulation is the only update we need in memory. Besides copying the type buffer to the GPU, because that is how we're defining if a voxel is going to be rendered or not, right? Which we would have to do anyways before. At any part of our pipeline, that ID needs to get to the GPU just so we can know if a voxel exists or it needs to be textured, right? And actually, you could even do an optimization where you took a bit array, uploaded that, use that to test if it's air, and if it is air, don't texture, but if it's not air, you just have an adjacent buffer that's sparse with the types, and then you could get those types. So lots of optimizations here, right? So instead of having to worry about meshing at all, the simulation is the update itself. That means we could have massive world updates and not worry about meshing. We can set SDFs, run large simulations like a huge game of life, and do whatever we want, basically. And this is really powerful when you consider that also the only thing determining which voxels we're sampling is an index. We have our chunk index and our voxel index, and those combined tell us what voxel we're indexing. So like I said with that rolling procedural world example, if we load more chunks, all we have to do is say, hey, when we're meshing, add this offset to our chunks, right? Statistics. So I've talked about statistics a lot, but we took a 3 to 5 milliseconds time to mesh a 64 cube chunk with not reducing faces at all, down to 0.12 milliseconds or 0.01 milliseconds in the best case scenario with binary greedy meshing. Then we realized we didn't have to mesh at all. We didn't have to do any of this work in the end. We've completely reasoned that away, which is really, I think it's cool. Yeah. So let's solve some problems with the global lattice and also some optimizations. Let's first talk about a solution for floating point precision, which I call the treadmill, right? With a rolling world that moves so quickly and such big faces representing our geometry, like it could be 0 to 8,192, and when you're using world space positions to sample what type of voxel you are to mesh, or to render, sorry, all we have to do, we run into floating point positions very quickly because when you move further away from the origin or 0, 0, 0, things get very janky very quickly. So voxels will like bleed into other voxels and it looks super awful. So to fix this, instead of actually moving the global lattice in the world and using the world space position to index the chunks in which voxels we render, all we have to do is let the player move in a single chunk at 0, 0, 0. So they're always in this range, and this is arbitrary. It could be any region, but we could just always have the player be in this, like, let's say it's just a single chunk, 0 to 64 cubed, and rolling in this chunk, right? So when a player crosses the chunk's boundary in any given direction, we take which direction they moved in and turn that into a chunk indice using that same way we composed our chunk index. We can just add 1 to x, turn that into an index, and add that to the chunk index that's being sampled on the GPU. So we just add an offset based on the direction that they're going. You can see that here. Since x was our first, or our highest priority axis in constructing our index, if they moved in the positive chunk direction of x, we would just add 1 to the chunk index offset, which would be added to the chunk index on the GPU that's being sampled. So now the world is always located at 0, 0, 0. It's local, but we can still go through the entire world, no problems. But it's really powerful because now we don't have any floating point position when we load noise, so there's no like far lands if people are familiar with that term. So now we can just have a truly infinite world. We just have to generate the noise. So another optimization I'd like to talk about is maximizing what's in view with Frustum rotation. Right now, at any given point, the player is only seeing about 2 quadrants of our Frustum, or our camera view. The camera view is only looking into 2/4 of our actual global lattice of our scene. So an optimization we can do is, let's say the player is looking in the bottom left corner. What we can do is we can project where they're looking onto an inner boundary and almost flip the scene so that instead of looking out into the scene, they're looking into the scene, right? So instead of only looking into 2/4 of that Frustum, we can have them we can maximize the amount they're looking at any given time based on their field of view. So we can move that inner boundary there based on their FOV. So we can see that their FOV is never going past this corner, which means they can't see any clipping in the world or edges, right? So it's just a seamless world. It just looks like it's infinite in that direction. And if we have and that's a pretty extreme FOV. So if you have an even lower FOV, we can see that they're even closer to this border. So instead of the player rotating around the center here, we project where they would be looking into and basically render the world back at them in a way. So we're maximizing the amount of the global lattice that's being rendered at any given time, right? Which is a really cool optimization. So in conclusion, I want to reflect on the kind of progress that we made while meshing and going through this entire process of optimization. A lot of times, we wouldn't even have made any progress or learned anything or found out that we could do better than we were doing if we didn't take a step back and think that we could do better. So I want to mention that a lot of the time, I think a lot more is possible than people realize or initially think. And I think this is something that this taught me. I was a beginner programmer around 3 years ago when I started making these voxel engines, and I had a lot of preconceived ideas. So I was holding on to those for a long time, then eventually you just ask yourself, wait a second, why do I have to believe this? And you can do so much more. And the thing is, it's not hard. You just have to think you can do it. There's like 1,000 billion ideas that anyone in this room could absolutely pursue and find a lot more value there than what's previously found, right? Which is really cool. Like the end goal is never obvious. If we never pursued the binary greedy meshing, we would have never found out that we don't need to mesh at all, right? So I also want to encourage people to find a topic or technology that interests yourselves and to pursue that in this kind of way. See how far you can push it, because a lot of the time it goes further than you might think. And also, when you pursue an idea like that, you understand the problem very deeply, which means you probably understand the computer very deeply, right? Because that's hand in hand. And when you have that kind of relation, you can take that your specific knowledge and generalize it to new problems, where if you're working on something new and it's like, oh, this is kind of similar like that with that thing that I did over there, and I know a lot about that thing, so now I can take that very specific knowledge and apply it over there, right? So you know what parts are fast and why, allowing you to take your specific experience and use it to relate to new scenarios, right? So I kind of sped through that one, but thank you all for listening. I'm Davis Morley. That's my Gmail if you want to contact me. That's also my Twitter. I think I'm supposed to turn it over to Avner for Q&A. Yeah, thank you. Thank you.